All right, there's a handful of things I want to touch on with the linear function first. And so let's look at it over here really quickly. Just one note, be careful about this. In general, make sure it's very clear that our x is a little bit higher up. That way it's clear it's being multiplied. Otherwise, it could almost start to drift and look like that x is where? With the 4, so dividing by x. We're not dividing by x. That gets into a whole new set of functions that we don't study, at least this year. So just be careful about that we're not putting that into the denominator. Couple of things I want to point out and I want us to note here is, let's even look right here at this one. So I talked about this point with this group, but I didn't talk about this one. First things first, actually, do note y equals mx plus b. We want to recognize linear. But does this look exactly like y equals mx plus b? No. Why did we put the y-intercept at 2 even though typically the slope is first? Yeah, but like my point is like typically we have our slope first, so why'd you put the y-intercept at 2? So yeah, we need to recognize that mx, right? And this is b. So here's my mx. The other thing to remember is this. Demia, how do we mathematically show repeated addition? Multiplication. So this right here is my multiplication. We want to recognize that that multiplication is what's really defining my slope. Because that means I'm repeatedly adding what? What am I repeatedly adding? Say louder. Which? What numbers? 3/4, thank you. We'll talk more about that in a second, but we want to notice that that is not my b, that is not my slope. This is my y-intercept. This is my slope. And you can just reorder it. But yeah, 0, 2. Now, this group originally had their points switched, and I wanted to talk about it even in respect to here. What this is saying is that -1 is the what for that point? It's an input, and it's mapping to what output? -4. But we need to check that. For those of us who are getting lost and struggling a little bit, don't forget that you can always substitute inputs in and get outputs out. Now this would give me 1 1/4. Is that what that output is? 1 1/4?
Yes.
This output says 1 1/4. It says -4. Yeah, not the same, right? Be careful about your points though, because this point is correct, except that's not the point -1, -4. What is that point? Remember, x first, then y, so left and then down. And if I switch this to a -4, I now have 2 minus 3. And what's 2 minus 3? That's the -1 output that we want, right? So this line is correct, but be careful with those points. I do love that this group labeled their points, though. That is something to pay attention to for sure. But I want to contrast that with this group over here. We need to be careful. This group recognized m is 3/4, but remember, how do we calculate our slope? Because notice, they got very different points, right? How do we calculate slope, though? So what beautiful mistake did this group make?
They made 3 the y.
They made 3 the x, right? And 4 the y. Be careful about that. Make sure we pay attention to that. And that also goes back to the idea of, guys, take a second to substitute your input in to check getting your right output, right? Label these things. Be careful about these things. Because they even substituted this 3 in. And when they substituted 3 in, did y'all get 3.5 out? No. Hold on. 2 plus 9/4 would be 5.25, which is not 6, is it? So take the time to actually substitute your values in and check yourself with those. But rise divided by run, or change in y divided by change in x. Check your points, be careful with that. What are your questions about that linear one? I do want to point out and emphasize what this group here did. I really like this. Notice they made their table, right? Except that they did the same thing with the y's and the x's as well, right? But again, this is where just taking a second, substituting your inputs in to get your outputs out will help in checking it. But do not forget, slope is calculated as the change in y divided by the change in x. I am very glad that I did this review before our midterm on Friday. All right, what questions do you have about this linear function before we continue to the exponential? Do y'all want to take a couple minutes to write notes to yourselves about this linear before we continue to the exponential, for those of us who struggled with it a little bit? I'm not getting any yeses, so I'm going to continue on. We're just going to trust in our memory after all this time of struggling with linear. Okay, just continue on or take notes. Okay, then say that. Let's take a couple minutes. Let's write this problem down, write down the table, write down the graph, just to help it settle in. And don't forget that note of can always substitute inputs in. But guys, we got to know linear, what, mx plus b, m is that change in y divided by the change in x. This is a question that I want to extend to you, and this will, if you want to take this time to do some more notes on the linear, you can, but I want us to discuss really quickly, how could you find the x-intercept of this? Because very clearly, right, not a perfect number. So how could I find the x-intercept of this linear function h of x? Go backwards, make your y what? 0. Can we make y 0? Is that legal? Yeah? What do we know about every x-intercept that's ever existed? The y 0, the output is, okay? So really quickly, I want you to just work for a second. I want you to find what your x-intercept would be in this linear function. So subtract? Subtract what? So what are you using to find your x-intercept? Inverses? Don't forget, like, you can do it in other cases, but if you only see that variable one time, what can you always use? Inverses, starts with an I, it's inverses, with your properties of, gotta know those. All right, now one thing I will point out is I saw some students dividing by 3/4 here, which sure, that's legal, but what would be easier than dividing by a fraction? Remember, this is why I really like that reciprocal right here. 3 divided by 3 is 1, 4 divided by 4 is 1. And then this takes care of a lot of the issues with a lot of us. I know a lot of us wrote negative 2.6 repeating or 0.67, yada, yada, yada. But guys, what's negative 2 times 4? Negative 8 divided by 3. Done. When I came by and said, hey, how could you write that more easily? Just write it as a fraction. Just like we leave it as a square root, right? The common thing in mathematics is to leave fractions. Okay? You can get a decimal if you're trying to do it by, be able to graph it, but do note, it'd be negative 2.6 repeating. Does this look like negative 2 point something? That x-intercept right there? Yeah, 100%. Remember, that means that if you substitute this in, what should it make the output? If you substitute negative 8/3 in, what should the output be? 0, right? The whole point is it's a 0, right? You can also check it graphically, all those fun things. All right, from there, that was just a little extension, but note, even for linear, it should look like that. Now, this one, the exponential, I want to talk about a little bit more clearly, a little bit more in depth. Not in depth, really. Just focus on some details. This one, I also switched the order. Typically, it's a times b to the x, right? And so how do we know this is an exponential?
The exponent.
The exponent is a x, or a variable, just in general. It could be things other than an x. And notice that matches this piece. And we got to remember, why is it called an exponential, Davis?
And multiplicative rate of change.
As that multiplicative rate of change. And how do we show constant and repeated multiplication through an exponent? It's like when I look at that equation, what am I repeatedly multiplying by? 2. We want to recognize that that's being constantly and repeatedly multiplied by 2 based on the structure of this, right? Understanding that that exponent is repeated multiplication, I'm multiplying by 2, which makes this 3/4 my what? Y what? That's my y-intercept. Notice, and I think a lot of students didn't quite do it at first, but if we substitute 0 in, what do I get out? 3/4. And I want to just point this out and remind you over here, so I'm going to draw it a little bit bigger. But I asked this group over here, and I said, hey, what is 2 raised to the 0? And they got the most common error. I love it. It makes sense. The way we think 2 to the 0 is 0. That's the most common mistake with that, right? But remember, I showed you all this a few times already. We already know a positive exponent is repeated what? Of exponent. Multiplication, right? So what are we doing? We're multiplying by how many 2's? 2 2's. But that's why I start at 1, and then I literally multiply by 2 2's. 2 to the first, I am taking 1 and multiplying by how many 2's? 1 2. What if I had 2 to the negative 1? That was not multiplication, but starting at what number? 1 divided by 1 2. So what does an exponent always start with? 1. And I just don't have any 2's, right? So anything to the 0 power is going to equal 1. Anything to the 0 power is going to be 1. You always started at a 1, and it's how many times you're multiplying or dividing by that. Which is why, when we do 2 to the 0 times 3/4, what's 1 times 3/4? 3/4. And then what are we constantly doing? Multiplying by 2. 3/4 times 2 is 3/2. 3/2 times 2 is 3. If you go backwards, you'd have to divide by 2. But again, this is why I like those reciprocals. That's way easier than dividing by 2. Dividing by 2, a lot of students make mistakes. But notice what's 3 times 1? 3. 4 times 2 is 8. So 3/8, 3/16, and so on. But just remember that it's a constant factor. It's what we are repeatedly multiplying by. Okay? What are your questions through here? Understand the exponential? Let's jive with what we remember, hopefully. Yes? You have a question, David, and you're like, yeah, I remember. Okay. We're going to continue with some quadratics in a second, but one thing I wanted to point out, I want you to be careful of, so like right here, that's what I was looking for. Notice that 3/4, is that an x or a y value? That's x, but what is it supposed to be? Be careful, right? 3/4, 3/2. Yikes. Why I gotta break my stuff? 3, just give me a hard time. -1, 3/8. Do you remember these exponential? What do they never actually touch or intersect? The x-axis. They get really close to that x-axis, but they never quite get there. And the way that I explain it to really make it make sense is this. If I'm constantly multiplying 2 positive numbers, what are those always going to stay? Positive. It may get really close to 0, but it's never going to get there. Right? It's always going to stay positive. I can't remember if I introduced this word before or not, but in a couple of units it'll come back up, so I'm just going to go ahead and introduce it. This x-axis is an asymptote. So you don't need to stress that right now, just be aware it's going to come back up. What I mean by an asymptote is that function is approaching it, but it never quite gets there. It's approaching at some infinity, but it doesn't quite get there. And the reason why I say some infinity is what's x going towards? What's the x value all the way over here? Not infinity, close. Remember, if I'm going left, what's it going towards? Negative infinity. Remember, if it's going to keep going left, keep going left, keep going left, keep going left, and it never stops, what number is that, or concept is that? Negative infinity. So, as x goes towards negative infinity, that function is approaching the x-axis. Doesn't get there, but it approaches. That's why I call it an asymptote. I'll talk more about that a whole lot later. Again, you don't have to know the asymptote, but you do guys need to notice a constant factor. You need to notice the y-intercept, and that's way easier than just doing inputs and outputs. Check yourself, but with knowing the constant factor, knowing the y-intercept makes this way easier. What questions do you have? Okay. Give you a couple of minutes to write down any notes you need to about these exponentials, but I'm glad I did this because this is on your midterm. You know you're struggling with linear and exponential, creating graphs and tables, or creating equations from graphs and tables. Please make sure you're doing those check your understanding questions associated. So whatever notes you need to about the exponential. I got this, which can't I study, take notes, that's overrated. From what notes? Okay, just from before, you're just going to trust in those. I respect it, I guess. Reuben Roosevelt McDaniel. So, one, I have to go back and look. I feel terrible I didn't write this down. I want to say he got his PhD in like the 30s or 40s, like 1930, 1940. He was the fifth, I want to say fifth African American period. Yeah, actually I know that's true because there's no women who had PhDs at this point. So fifth African American to get their PhD in mathematics. So he studied should say high school. He studied at Hughesville School for 5 years. I didn't know this until I started reading about his life, but apparently at this point in time, black students went to school for 5 years and white students went to school for 6 years. At least that was what was mandated, and that was it. Obviously very inequitable in the fact that black students got less education. And that was all that was mandatory. Immediately after he finished his 5 years of elementary school, he went and started working with his father on their 75-acre farm. And one of the things that was very interesting to me about this is he started having ideas about how to get better crops, better yields, how to do things in a more efficient way. And his dad wasn't having any of it, right? So Dr. McDaniel was reading articles about how others were finding more efficient paths, and his dad was like, look, this is the way I've always done it, this is the best, we're not changing it. He's like, I have experience with farming, so I'm not going to listen. And so that actually ended up fracturing their relationship. He moved to DC to live with his sister, and while he was there, he took a job delivering mail. He was not content with staying there his entire life, and so he actually met someone who helped him go to or finish out his elementary school at nighttime, and then started working through high school, worked through his college, and got his PhD. I want to say, no, it was Cornell University is where he went to get his PhD. And so it's just one of those things that I loved how his discontent for the status quo is what drove him to do more. And so one thing I want to encourage you is, don't be satisfied with the status quo. Don't be satisfied with what's normal, but shoot for more, because that's when we become the best versions of ourselves. You can always do more. You're always capable of more. And don't be scared of going outside of the norm. There were better ways to farm, and his dad wasn't listening to any of that, and so his dad was not able to grow. Encounter something different. Challenge yourself to go beyond. The other thing, the reason why I did select him is his PhD, his thesis was all about approximation to algebraic numbers by means of periodic sequences of transformations on quadratic forms. Whew, that's a mouthful. But the focus for me was this: algebraic numbers and quadratic forms. His entire PhD thesis in the early 20th century was about how do we approximate the roots using the forms of quadratics. In the early 20th century, we were still trying to figure out how do we approximate things like the square root of 2, the square root of 3, 5 root 5. These are what we call algebraic numbers because they come from solving polynomials. So an algebraic number is just a number that you can get by solving a polynomial. There are a set of numbers out there called transcendentals, is that right? That are not algebraic, don't sweat it. The whole point is, even in the early 20th century, we were using quadratics then to understand these numbers better. And so his whole thesis was on that. The stuff that you are studying today is what we looked at in the early 20th century and were able to write an entire thesis about. So, what you're doing today is good and it's worthwhile and it's useful. And so, just want to encourage you with that. Just be aware that math is one of those things that's always being learned and developed. These aren't rules that were developed 1,000 years ago. They're constantly being discovered, and you can be a part of that process. So, thank you all for listening to Mathematician Monday. Complex coordinate system, we're all about the number I today. Remember, our goal is that we can add, subtract, and multiply imaginary numbers, graphing imaginary numbers, solving quadratic equations, simplifying square roots with negative radicands, and then classifying numbers over the complex number system. So, let's do a quick little review with part of this. First things first, 5 minus 3i. What part of that is the real part of that complex number?
5.
The 5, and the imaginary part would be the 3i. Okay. So then, let's say I have this. Anybody know what the complex and the real part of this number would be? 2i times 5 minus 3i? Would I need to multiply those? So notice this is not simplified. If I want to know about this number, I need to simplify it. Okay, so what would I get? 10i
6i squared.
plus 6i squared? So minus 6i squared. Okay? So what's my imaginary and what's my real?
The real is a 6i squared because if you square it, it'll come out as a positive.
Wait, so say that one more time, Jaden.
If you square it, it'll come out as a real positive number.
Oh, close. Super close. And maybe you're right on that language. If I square what? Does anyone remember what I squared is? So remember, I squared is what we defined as -1 so that I is equal to what? Square root of -1. Okay. And so, just make sure you follow this all the way out, because what's a negative times a negative? And so I would rewrite it this way. Remember, we always put our real part first and then our imaginary, so the real part of that number is actually 6, the imaginary part is 10i. So make sure you simplify your numbers before you try to do anything else, right? So before you try to classify or anything like that, make sure you simplify your numbers. Fundamental theorem of algebra, that's pretty critical. What does that fundamental theorem of algebra tell me about this function? Does the fundamental theorem of algebra tell me it's in standard form though? It tells us that it has what?
2 roots.
How do you know it has 2 roots?
Squared.
The squared? So what is that fundamental theorem of algebra telling us? Okay, let me contrast that here. How many roots do you think this one would have? 5 roots? Because of this 5? Is that why? I'll confirm this. It has 5 roots. So what's the fundamental theorem of algebra telling us? How did you know that this had 2 roots and this one had 5 roots? Okay, so maybe it's whatever the greatest root is of all the roots. Can anyone build on that? Add on to, push back on that? Maybe just language, whatever. Look at the language. Think about that language. Shadisha is saying that maybe it's the greatest root for each of these. That's how many roots it has. Greatest exponent, greatest, starts with a P that we usually use. Power. Okay. So it's the greatest power on our variables. So notice the greatest power tells us how many roots. Does that make sense? So that's that fundamental theorem of algebra. Just whatever the power is, the highest power, that's the number of roots. Now, I do want to point this out. We just said that f of x has how many roots? 2? Let's check this. Was that 5x squared plus 7x plus 8? Does it look like it has 2 roots to you? No? Why not? Why does that not look like it has 2 roots? It doesn't come close to what? X-axis? So does it still have 2 roots?
Yes, but they're imaginary.
Oh, that's right. The x-intercepts are just what type of roots? The x-axis. Oh, those are the real roots, right? The x-axis shows me the real roots. It still has how many roots? 2 of them. They're just imaginary. They exist. They're actual numbers. They're just imaginary numbers, imaginary roots. Does that make sense? So like, don't forget, those are 2 very real roots. They're just imaginary. Actually, reword that. They are 2 roots that exist, right? They're not real numbers. They are imaginary numbers. All right, let's contrast that actually with this. All right, x squared plus 4x plus 4. How many roots do we think it's going to have? 2. Okay, we all give it 2? In agreement? Oh. Oh. What do you think that means? It is the vertex, isn't it? So what do you think that means? Going once, going twice. Any guesses? I wonder this. I wonder if a different form of that equation might reveal something else. What form do I have of that quadratic right now? Standard. What's another form I could use? Vertex form? Because you're looking at that vertex, right? Okay. All right, so what is h? How am I going to calculate it? Opposite of
B over 2a.
By the way, do note, I know that this is a slightly different way to get there, but I'm trying to help us review some of these ideas with quadratics by creating these situations, okay? So opposite of b divided by 2a, so negative 4 divided by, that's not a 4, negative 4 divided by what?
2.
2? 2 times 1 or 2, yeah. So there's h. How am I going to find k? So don't ever forget, an input of h gives me an output of k. So f of negative 2 equals that thing, plus that thing, plus that thing. What does that equal? So the vertex form of this would be x minus a negative 2, so x plus 2, squared, and then k would be 0. Do I even need to write that plus 0? No? Okay. Or in factored form, those are all the same thing, right? How can I check, by the way, that the vertex and the factored form are equivalent? Say again? Thank you. Guys, one thing you have to show me on the midterm is that you can identify equivalent forms or functions. Yep, that maps. So all three of those forms, they map to each other, don't they? So I want you to look at this right here. Because I will say this factored form, now I know like vertex, it makes sense because like, oh, we're looking at that vertex there, but what did we talk about? We wanted to look at the what of that quadratic. It starts with an R, the what?
Roots.
And where do we see the roots most easily? In factored form. So what do we see about those roots? What does R1 equal?
Negative 2, 0.
So it gives me an output of 0, but R1 is negative 2, R2 is...
Negative 2.
So let me ask you this, are there still two roots? But what's unique about these two roots? Okay, or what? So, I'm trying to think if we would say that they're equivalent. So typically when we say equivalent is they look different but they're telling the same story. Do those look different? No, so we would just say that they are what? Equal, right? Like they are the same. So yeah, I like the idea of equivalent for the same, but in this case they're quite literally the same, right? They're both negative 2. So we're going to explore more about this in the next unit, but we would call this a double root. Notice in the past, at our roots, hasn't the parabola gone through the x-axis and then come back up and gone through the other x-axis? But what's it doing when it's that double root? How would you almost describe that? Huh? Yeah, so like think about a ball though, right? Like what would a ball be doing? Think about, you throw a ball, it hits the ground, and then it what? It bounces. You know what we call this? Guys, come on, why did I get you to that word bounce? What does it do?
Bounces.
It bounces. That's it. Think like a ball. Like if I take a ping pong, toss it, hits the ground, and then it bounces. At that root, or that x-intercept, the graph is just bouncing. That's a special piece of a double root. So, big idea, things I want you to recognize is, it doesn't matter how it looks, every quadratic has how many roots? 2. They could be, from that earlier one we had, they could be, what kind of roots did this one have? Remember when I graphed it, it was all the way up here. Imaginary. They could be the same where it's a double root, or it could just have 2 different roots. We're going to study a whole lot more about roots moving forward, but I just want you to recognize every quadratic has that many roots, and again, every form reveals its own piece of information. Do not forget how to convert among the forms. Make sure you study that and you know that, because it's going to impact what we do next unit a whole lot, and it's on the midterm. What questions do you have for me at this point? I know we probably need some more practice with imaginary numbers. Is that fair? Okay. So we'll do some practice with imaginary numbers. And to save some of you the headache, what I'm going to do is we're going to solve these 3 quadratic equations in class. and then we're going to work on Mathia, meaning that tomorrow we're going to start with the what? We're going to start tomorrow with the demonstrated understanding, okay? So we're going to work on solving these 3 quadratics in class. We'll discuss, we'll break it down afterwards, and then we're going to get our iPads out and work on Mathia. Sound good? All right, let's get to it. By the way, this is page 109 from the textbook. Quadratic in standard form. What are the methods to solve a quadratic in standard form? If I gave you a quadratic in standard form, what could you do to solve it? So you can convert it to vertex form and use, if we got vertex form, what can we use? Inverses, right? If you want to look over here at the group of tens, see how they converted it to vertex form? In red there, they got h and they got k, and then what did they start using once they got 0 equals x minus 4 squared minus 34? They started using inverses. One thing to be careful about, because I just noticed this, make sure you have your negative in front of those parentheses, because the a is a negative here. It is negative x squared minus 8x minus 18. It's not going to change your time, but we'll talk about that a little bit later. All right, so keep that in mind. But we can convert it to vertex form and use inverses. What else can we do? Factor it and use the zero product property. But Elizabeth and Bella, y'all kind of look at each other laughing. Y'all tried factoring it, didn't you? Did this one work? Remember, guys, if I'm going to try to factor, even before I start to draw that area model out, I'm going to take a times c. There's 18. Are there factors of 18 that add up to a negative 8? Because I need factors of a times c that add up to what? B. Negative 8 in this case, b. And there's nothing there, right? I got 3, I've got 6, I got 9, I got 2, I got 1 and 18. And nothing's going to work out for me. Doesn't work, all right? So can we factor it? No. Which I will point this out. Remember, this is all about some imaginary roots, so that probably explains it. But last method that can always work is that quadratic formula. Don't be scared of it. The only thing with the quadratic formula is you are going to have to, which I'm going to rewrite it here. Make sure, by the way, on your test, please just write out the formula. 1, it's just a small piece of evidence of understanding. And 2, it's going to help make sure you don't make mistakes with it. By the way, how many methods do you have to have for your test to show proficiency or get to the target? 2. If you show 3, then that's what gets you to the exceeds. But right here, this is what I want to focus on. Once you have this written out, just type that entire, what do I call this thing under the radical again? Radicand. Type the entire radicand into the calculator. Remember, it's a special one, also called a discriminant, right? That's in the textbook, the discriminant. And so we get the square root of negative 8. And so I had some people looking at me. I saw at least one group try to take this negative 8 and divide it by negative 2. But remember, a square root is a whole lot like something that starts with an e. It's a whole lot like an exponent. Remember, we talked about this a little bit last week, where this tells me that it's the second root of negative 8 to the first, right? So can I divide before I do an exponent? No. We need to simplify. So be careful. I don't remember which group I saw doing this, but you cannot divide this negative 8 by the negative 2. We need to simplify the square root of negative 8. So what can I do with radicals to simplify them? Say again? What can I do with those square roots to simplify them? Say again? Yeah, I don't just turn it into an I though. What do we do to get to that I? So we split into our factors, and you said, I heard negative 1, and you just said 8, but are there any factors of 8 that I can take a square root of? Say again? So I can split into 4 and 2. Which of those can I take the square root of? 4. So remember, split your factors up into a perfect square if at all possible. If there are no perfect squares, that's fine, but I can take the square root of 4. What are some other things that I can easily take the square root of? 1, 4, what would be the next one? Before 16. 9, right? 1, 4, 9, 16. Where am I getting these numbers from? What is this? 1 squared. This is 2 squared. Etc. Because those are the things I can take the square root of, right? Square root of 9 would be. Square root of 9 would be 3. Right? What was squared to get 9? 3. So the square root of 9 is 3. What would the square root of 6 or square root of 36 be? 6. Right? Whatever factors you can easily take the square root of. Yikes. So remember, I take that time, and I will cover this up before the test, but it's also still over there right next to Landon, where I show a few examples of simplifying radicals. You can walk. You got legs, yeah? Yes. All right.
You guys have to be that scared of the
Square root of 4, what is it?
Go back. Go back.
Square root of 4. 2. Square root of 2. Be careful. It has one. It's just what? It's not just. It's an ugly decimal. What do we call that?
Irrational.
Which one?
Irrational.
Irrational, right? It's not rational. The decimal does not terminate. It does not repeat. So it's just the square root of 2. Square root of negative 1 is I. 2 root 2 I. That's what would be right here. 8 plus or minus 2 root 2 I divided by negative 2.
So anytime we have the square root of 2, it'll always be 2 root, or whatever you just said.
Square root of 2?
Yeah. Like anytime we have it, it'll always.
If it's not a perfect square, just leave it as a square root.
Okay.
So if it's not a 1, 4, 9, 16, 25, 36, 49, 64, 81, do you get it? We get it now? Okay. So if it's not a perfect square, leave it as a square root. But find your factors that are perfect squares ideally, okay? So, because then I can divide by that negative 2 just to simplify it. Notice I'm just distributing my division, because that's essentially what that is, right? Division is multiplication, so I can distribute division, just like I can distribute multiplication. This is the answer I would have gone with, once I simplified everything. That's what x equals. But, you know what could have saved me a lot of that headache and made it easier to get to the final answer? No. Put it in what? So remember, the beauty of vertex form is there's less simplifying involved. That's why I like vertex form a whole lot, is because there's less simplifying involved. And that's pretty much it. Yeah. Any questions about this one? Ready to move forward? All right. So move on to whatever the next problem you have is. Mr. Hobby and I will still be coming around and working with you. There's a whole lot less simplifying. That's the reason why I like that vertex form. But, for those of y'all like, man, those are ugly numbers. I get it, right? Imaginary numbers are not what we're used to. Irrational numbers, not what we're used to. But if it's a 0, and you substitute that number in, what should you see? Guys, if you have a 0, and you substitute that in, it should make the equation equal to, well, it should make the equation equal to 0. So if you set it equal to 0, it'll say true. Right, so remember to check yourself on the demonstrated understanding on the assessment. You're going to have a calculator, okay? So make sure you keep that in mind. We did not have a chance to get to the Mathia. However, on Mathia, there is practice with imaginary numbers, things like that. Make sure you take advantage of that tonight to get ready for your demonstrated understanding tomorrow. Tomorrow, we're going to start with the demonstrated understanding. We'll go over it to help you prepare for the midterm. I'm going to give you all 20 to 25 minutes in class to look at your proficiency scales that I've done for you. Note what you need to work on before the midterm. And then we're actually going to get started a little bit into the next unit because next Wednesday is going to be an e-learning day. So I need to take a little bit of time to start, for the vast majority of us, I think we've got a couple sophomores that have to take the pre-ACT. Yeah, y'all are going to have Monday through Wednesday off.